We have already discussed particle motion using derivatives, but now we're going to include integrals in that discussion as well. So at the end of this lesson, you'll be able to analyze a particle's motion using calculus concepts. All right, in questions about particle motion, the particle may be moving in one dimension along a line, usually the x-axis, though it could also be moving along the y-axis, and it will usually tell you in the problem. The particle may also be moving in two dimensions, in which case it might be referred to as a freely falling object. Again, we've discussed some of this particle motion before, but now we actually can go both ways with particle motion. All right, just a few things, and again, a lot of these things will be a repeat. The position of the particle, and it's usually denoted by x of t or s of t. A lot of times we'll do x of t if the particle is moving along the x-axis, is basically just its location on the number line. Position is expressed in linear units, such as meters or feet. All right, the next one is the velocity of the particle is the rate of change of position with respect to time, or it's the derivative of position, and again, we've already had that. Velocity just tells us how fast and in what direction the particle is moving. Velocity is expressed as a ratio of linear units and time units, such as meters per second or feet per second. And then the acceleration, whoops, nope, that's not where I want yet. The speed of the particle, and we've already discussed this as well, tells us only how fast the particle moving, and speed is the absolute value of the velocity. So it doesn't consider direction. Okay, and then the next one is the acceleration of a particle is the rate of change of velocity with respect to time, or the derivative of velocity, or the second derivative of position. Acceleration is expressed as a ratio of linear units and time units squared, such as meters per second squared or feet per second squared. So that's all stuff basically you've had before. This is new next. Now the distance traveled by the particle is going to be the integral of the absolute value of the velocity equation. So it's going to be the integral of the absolute value of the velocity. So that's what we will use, and we'll have a number that goes here and a number that goes here. So let's try some problems. Not quite yet. All right, particle velocity, just to clarify, and again, we've had this before, but let's just clarify it. If the particle is at rest, the velocity would equal 0. If the particle is moving to the right or up, the velocity is positive. If the particle moves to the left or down, we know that the velocity is going to be negative. And if the particle changes direction, the velocity must change sign. And those are the same things that we do if a function's increasing or decreasing, exactly the same concept. All right, example 1, suppose a particle is moving along a line with its position at time t given by this position formula. Find the velocity of the function. Well, if this is position and I need to get to velocity, I know that velocity is going to be the derivative of the position, so my velocity formula will be 3t squared minus 3. And we don't have to put a plus c this time because we are taking the derivative. All right, now it says to find the velocity at 0 and 2, so I'll just plug 0 into my velocity function, and that gives me negative 3. And we're in feet in seconds, so this will be feet per second. And the velocity at 2, we'll just plug in 2. And when I do that, I'll get 12 minus 3, I'll get 9. And again, it's measured feet per second. All right, when does the particle change direction, and where is the particle when it changes direction? So first of all, let's figure out, when does the particle change direction? Well, we know the particle changes direction when the velocity changes sign. So just like what we did when we were going increasing and decreasing, what we're going to do is draw a derivative chart, which in this case will be a velocity chart, because in this problem velocity is the derivative. So first of all, we need to figure out, where does the velocity equal 0? So I am going to maybe go over here. The velocity, we need to figure out, where does it equal 0? So I'm going to actually add 3 to both sides, divide by 3, and then t would actually equal plus or minus 1, but since we're talking about particle motion and time, we're not going to go into negative time, so t equals 1. And now, just because I get t equals 1 as my critical number doesn't mean the particle changes direction. We do need to test it to make sure the signs change. So if I put in 0 into my velocity formula, I will get a negative number. And if I plug 2 into my velocity formula, I will get a positive number. So I can say the particle changes direction at t equals 1, and that would be because the velocity changes sign. And I definitely would have to check to make sure it actually changes, okay? Then the next part of that question says, where is the particle when it changes direction? So the next thing that I am going to do is, if I'm talking about where, I'm asking for a position, so I basically just need to find the position at 1. So if I plug 1 into that equation, I'll get 1 cubed minus 3 times 1 plus 2. So 1 cubed is 1, minus 3 is negative 2 plus 2. My position will be 0. So we would be done. It's just going to be at 0 for the position. Right, let's write a description of the motion of the particle from t equals 0 to t equals 2. So if I want to know, I'm going to refer back to my velocity chart here. It said 1 and then negative and then positive. Motion is just where is the particle moving? Is it moving to the left? Is it moving to the right? What's happening? Since the velocity is negative, we basically know the position is decreasing. So on this problem, we would know that the particle must be moving to the left. So we could say the particle is moving left on the interval 0 to 1 because velocity is negative and the particle is going to be moving right from 1 to, I'm thinking that did it give us, it said, nope, just t is greater than or equal to 0, so I guess forever and ever. So from 1 to infinity, the particle will be moving to the right, and that was because the velocity is positive. So basically the same thing that we did with our f prime charts. Okay, this last part says to find the distance traveled by the particle in the first 2 seconds. So I would like to find the distance traveled. We learned in just a couple slides ago that is equal to the integral of the absolute value of velocity. Okay, so we are going to do, and it was the first 2 seconds, so it will go from 0 to 2. So I'm going to plug in 0 to 2. My velocity formula was 3t squared minus 3. Okay, and since this is a calculator section, we could go ahead and use the features of our calculator to get this answer. We should end up getting an answer of 6. One thing that I will remind you of is to get to the absolute values, I went to math, and then I picked the number option, and then there was something that said ABS. So then we type in ABS, 3t squared minus 3, and that should give us the right thing. We will be saving example 2 to do in class, so I'm hoping that you can now discuss particle motion.